Hello everyone. So we have been discussing about caches, and we have looked a few aspects of caches, and today we will be discussing about different classification that are possible in caches, or different ways we classify caches. So let me directly jump on to the discussion. So what we are trying to discuss today is classifying caches. Okay. So as we have already seen that caches are nothing but small and fast memory between your processor and main memory. So I'll just quickly draw this for our reference. So we have this processor, and then we have our main memory, which is generally big and slow. All right, and in between we have caches, which is a small fast memory. Now the critical thing is this only keeps a copy of whatever there is in the main memory. So basically a small portion of main memory is copied here. Now you have to intelligently figure out what you want to copy here, because if the data is not available which you are looking for in cache, then you have to fetch it from main memory, and that is very expensive or time consuming. So the whole purpose of having this small fast memory is that so that you can get your useful data, or the whatever data the processor needs, available here, and you can speed up the performance. So what all the processor will provide? The processor will provide the address, and the cache will provide you the data. So basically this is address, and the data can go from memory, or basically come from the processor. Similarly, what is the communication between cache and main memory? So cache will be sending the address, okay, and then from main memory the data, and basically data from cache as well as main memory will be communicated. Okay, so this is what the uh, cache looks like. Now let's try to look at what are the different types of caches. Now the different types of caches can be based on certain things which the way the cache implements. So the first thing we will be looking at is how the cache gets populated. So basically there are different blocks of memory, and when you need to bring in data from main memory to cache, so how these blocks are placed in the cache. So depending on that, you can have a classification of caches. So we will discuss about it in detail, but I'll just write it down. So based on block placement, you can have different classification of caches. So and by block placement, what we mean, where can a block be placed where can a block be placed in the cache. So while you try to answer this question, based on that you can have different classification of caches. For example, if so I'm just giving you at a very top level, like if I can bring a block from main memory and I can put it anywhere in my cache, then that can be one type of cache. If I restrict that, okay, if this block you are bringing in, it has to go in a particular designated location in the cache and it cannot go anywhere else, then that can be a different kind of cache. And similarly there can be something intermediate where basically you restrict that, okay, if the block is coming from the main memory, these are the possible locations this block can be put in. So we will talk about them in our today's discussion. Similarly, the way the block is found in the cache. So basically, whether there is a block available in cache or not, how do you identify that? That identification, this whole process can also result in different classification of caches. So block identification. Okay. So how a block is found if it is in the cache. Okay, so based on that, again we can have different classifications, different types of caches. The next thing is block replacement. Now one is block placement. Now the next thing we will be talking about is block replacement. Now let's say you want to bring in some new block, but the cache is already you have some block where your new block is supposed to be there. Now uh, if there is a choice, for example, like you can replace uh, with the new block out of the existing blocks. Then if you have a choice, based on which how you exercise this choice, you can have a different classification. So we will be talking about each of these different classifications in more detail. I am just trying to introduce you the concept at this stage. So basically, based on the block replacement, you can have different classification. So which block should be replaced on a miss? So basically, whenever there is a miss, you have to uh, bring in a new block to make sure that you can address that miss, because your processor is directly talking to cache only. So if there is a miss, then you have to get the data from main memory to the cache, and then processor can access that data. Now think about a situation where processor requested some data, but that data is not available in cache, so there is a cache miss. Now in the block replacement strategy, you have to figure out, okay, I do not have that particular block, so I have to get it from the main memory. Now once I get it from the main memory, where should I put that block, or which block I should replace? Because there are already some existing blocks which I need to replace and then bring in the new data. So which block should be replaced on a maze? That answer will provide us different types of caches. For example, you can choose to randomly get rid of an existing block. That can be one classification. You can select some other ways. For example, if the block has not been used for very long time, then you can choose to replace that block and bring the new data and replace that block there. So these are all possibilities which we will be talking about in our subsequent discussion. And then the final thing using which we can classify caches is basically write strategy. All right. So in write strategy, we see what happens when we write something on the cache. So what happens on a write? So basically the processor wants to write some data. Now if the data is available in the cache, so do you only update it in the cache, or you also update it in the main memory simultaneously? Or if the data is not available in cache and you are trying to basically processor wants to write, so do you first bring the data from main memory to cache and then write, or basically you directly write in the main memory, or uh, or yeah. So these are the or basically if you are just writing it in the cache, then whether basically and do not update it into the main memory till that block is evicted. So that can be also one strategy. So these are the different write strategies, and based on how you handle write, you can have different types of caches. So I hope this at a very top level this overview makes sense. So we are saying that we are trying to classify caches, and the classification of caches will be based on how the block of memory is basically placed on the cache. So there are several ways, and based on that we can have different classifications for caches. How do you identify the block? So that is also basically can lead to different classification. Block replacement, so whenever you need to replace a block, what is the strategy you follow? Using that we can figure out like the different types of caches. And finally the write strategy, where whenever you need to write something in the memory, then do you only write it into the cache, or you write it into the main memory in one go, or if the data is not available in cache, then do you directly write it in the main memory without bothering the cache? So all these things are can lead to different classifications of caches. All right. Okay, so feel free to ask questions if there is any. Now we will be looking into each of these strategies. So we will start with block placement. So we will be now discussing about block placement. So the question we are trying to answer is basically where to place a block in cache. Okay. So let's say I have my memory, and the memory is divided into blocks. Okay. So for simplicity, or for this understanding purpose, we will keep the memory not that big. So this is our memory. All right. And the memory is divided into blocks, and let's say we have 32 blocks. So if I divide it into, let's say, half, so this will have 16. So I can further divide it into half. So I have now 4 blocks. So each block should have 8 blocks. Basically I'm just trying to draw it appropriately. So I now have 8 big blocks. Each of these big blocks should have um, 4 other blocks. Okay. So please draw with me, because that will help you visualize and also retain the information much more, compared to if you just observe and not actually do the activity. Okay. So what we have done, we have divided the whole memory into 32 blocks. all right. So we can number those 32 blocks. So basically this is the 0th block, 1 2 3 4 5 6 7 8 9 10 11 12 13, so till 32, basically 31 because we started from 0. Okay, so we have these different blocks. Now let's say now we have to draw our cache. So let's say this is my cache. Okay, and I have my cache which is 8, which can store 8 blocks. All right. So this is my cache which can store 8 blocks. Okay. Now so we are looking at block placement. So where to place a block in cache. So this is my memory. Let's say I want to bring in a particular block. For our example, let's say block 12 I need to place in cache. So I'll just highlight block 12 here. So this is the block of memory which I need to put in my cache. So one way of doing it can be that it's very flexible. This block can be placed anywhere in the cache. So I have like 8 positions where I can put this block. Now if I consider a situation where I can put this block number 12 anywhere in the cache, then this is one way of doing block placement. And if I have this kind of a block placement, then it is called fully associative cache. Okay. So what is fully associative cache? So all these blocks are capable of storing this particular block from main memory. So I don't have any restrictions. I can put this block anywhere where I would like to put in. So of course this looks like very intuitive and very good way to place your blocks, because you have to understand that how it makes a difference. Now in case of fully associative cache, I can decide that okay, I will place the block in a block which is, let's say, unused. So that can be one strategy, but or let's say the block which is least recently used, the block which is not getting used very much, I will replace that particular block in the cache with the new memory block from memory. And since I don't have any restriction, I can put it anywhere. So this block can be in any location. So that gives me lot of flexibility. But the challenge here is that whenever you are looking for a particular block in your cache, so you want to find that thing very quickly. So whether the data which you are looking for is available in cache or not. Now in this case of fully associative cache, since the block can be placed anywhere, so you have to look for each and every possible position to figure out whether the block you are looking for is available in cache or not. The other extreme, so this is fully associative. So block number 12 can be placed here, block number 12 can be placed in this block or here. So every possible block position is capable, and it can store the block number 12 in this cache. All right. So I can put block number 12 in any of these locations. The other extreme can be, again I have this cache which can store your blocks. So, it is basically 8 block cache, alright, and the block numbers in the cache are starting from 0, 1, 2, 3, 4, 5, 6 and 7. Now, in this case also, let us say I want to bring in block number 12 in this cache. Now, the opposite or the complementary complement to this fully associative cache can be a direct map cache. So, what is direct map cache? In case of direct map, the block number 12 is only restricted to go in a specific block among these 8 blocks. Now, how do you find which block it should go to? So, to figure that out, you can do a simple operation. You take the block number there and perform a mod operation with number of blocks which you have in your cache, so which is 8. So, if you perform this operation 12 mod 8, so you will get the remainder, and remainder here is 4. So, this remainder will tell you which is the block in the cache where you put this block 12, alright. So, in this case you will be putting your block 12 in block 12 of main memory into the block 4 of your cache. Now, look carefully, there is only one place the block 12 can go into, and that is why it is called set associative cache, direct map cache. Okay. Now, here you see that since several blocks can be destined to this same block in the cache, you might have a situation, let us say, where you want to place block number 4 into your cache. Then also you will see that block number 4 is directly mapped into this location. So, what if you have some previous data, you have to evict it, and if you need to bring block number 4, you have to put it in this block itself. Now, it might happen that the other blocks are unused, but in that case you do not have the flexibility to put the block in other blocks. You have to always put block number 12, block number 4, block number 20 in this block itself. Okay. So, you do not have flexibility. So, this is called direct map cache. Now, what is the advantage? The advantage here is that whether the data which you are looking for is available in cache or not, finding that out is very easy, because you know that if I am looking for a particular block number 12, then if the block number 12 is available in cache, then there is only one place where this can be, and this is the place. So, you just quickly check this location, and if you get the data, then very good. If you do not get the data, you know that the data is not available in your cache. So, this is called direct map cache. So, I hope this makes sense. So, this is very important. So, please pay enough attention. Okay. Now, then there is something intermediate, which is basically we do not want the rigidity of only one location where the block can be put in, and also the extreme flexibility where the memory block can be placed anywhere. Both of them has their advantages and some severe disadvantages. So, in this case, the time required to figure out whether the block is available in cache or not can be very high compared to a situation like this. But in this case, you will not be able to exploit the let us say temporal locality very effectively, because it might happen that right now you are accessing block number 12 and immediately after some time you need block number 4, then you have to replace block number 12 with the new block. And if again after some time if you want to access block number 12, then again you have to bring in block number 12 and replace this here. So you need to do lot of back and forth, which is not very basically which wastes lot of bandwidth, right. So you don't want to have that kind of situation. So is there an intermediate solution, or is there anything intermediate which we can think of? So the intermediate thing which we can come up with is something in between. So you do not have full associativity, but you also do not have direct map. So if we think it like this, let us say I have 4 such blocks, or 4 such structures where each of the structure has 2 blocks. Okay, and we number them as 0, 1, 2, 3. So here also we have 8 blocks, but logically we have created this subsets, and each of the subset each of the set contains 2 blocks. Now this is called two-way set associative cache. Basically this is broadly called a set associative cache. Now since in each of the sets there is 2 blocks, that is why it is called two-way set associative cache. All right. So now what is the advantage? In this case, again if we want to put block 12 in our cache, then we can find out what are the possible locations where block number 12 can go in, and to find that out we will be doing this operation. Basically 12, the block we need to bring in, mod 4, and that will give us the remainder, and remainder will tell us that which is the set where we can bring in the block number 12. Now in this case 12 mod 4 will be 0. So this is the set of blocks where I can put in block number 12. Now you see that you have the flexibility to either put the block here or here. All right. So that is better than direct map, because in direct map you had only one position where you could store, or you could bring the block, but here you have two possible locations, and you can select any of these locations to put the block number 12. Okay. So this is two-way set associative. Similarly, if I have a four-way set associative, each set will have 4 options where they can put their block. All right. So this is very important, and so these are the different classifications of cache you will come across, which is based on the block placement policy. So we are looking at block placement, and depending on the block placement policy, what are the different ways we can classify our caches. So that is what we have looked at. So among the different block placement policies, this set associative policy is the most popular one, and you will see a different set associative implementation. For example, i7, Intel's i7 processor is a 8-way set associative cache. So basically in each set there are 8 blocks which you can replace, and so on. Now in case of set associative cache, the advantage is that you will be able to uh, you do have the flexibility to put the block in not only one particular location, you have the flexibility that you can put it either here or here. So the advantage is that, like in the previous example we talked about, let's say I am dealing with block number 12 and block number 4, and I have to go back and forth for these two blocks. So in case of direct map, you have to, every time you have to bring in, let's say, block number 4, you have to get rid of block number 12 which was earlier there. So uh, so in set associative case, since I have two locations where I can put this block, so basically let's say block number 12 comes in and it observes that in this set the first block is empty. So that block can be occupied by block number 12, or that memory can be occupied by the block number 12. Now if I need to access block number 4, I do not really evict block number 12, because I have another location where block number 4's content can go in, right? So this way you have the flexibility, and you can achieve better performance using these set associative caches, and these are also very highly used caches. All right. Do let me know if you have any question, because this classification of caches is very important, especially with the block placement strategy, and you will be encountering this kind of caches, and they are basically you will be asked many times the difference between this fully associative or set associative or direct map caches. So please make sure that you understand it appropriately. All right. So now we will move ahead and we will see the next set of classification, which is based on block identification. Okay. So for block identification, so as we have already seen, we would like to know how to find a block in cache. So how to find a block in. All right. So basically, if you look at a cache, so you will have things like this. So let's say this is a cache. I'm trying to draw the cache block, or basically a cache. So let's say in case of a direct map cache, so direct map cache can be considered as, let's say, the sets have only one block in it, right? So if you remember, so for generality, I can consider that direct map cache is a associative cache where each of the set has only one block. Okay. So for completeness, we are writing that the set numbers. So let's say I have this cache where I have 4 blocks. Okay, so my drawing is not that consistent, so let me just leave it like this. So set 0, set 1, set 2 and set 3. So basically each block is only having one set. So now how do you identify the different blocks? So to identify these different blocks, you will have something called a tag. Okay. And then this is where the different blocks of data will be there. So basically this is your data blocks. Now let us say each block can contain 8 bytes of data. So basically each byte, if you want to specify, so let me just draw it. So each block will have 8 bytes. So I am trying to just highlight each of the bytes. So this is a byte, this is a byte, this is a byte, and so on, and there are 8 such bytes in one block. Okay, I hope this makes sense. This is making sense. So now to identify the cache, there will be how the block address will look like. So block address will have these things. So there will be a tag, then there will be an index, and there will be an offset. Okay. So basically the tag is used to check all the blocks in the cache, or in the set. So basically tags will be same for the blocks which are in the same set. So first thing will be, you will try to do is basically match the tag, and if the data is available, then basically you know that okay, this block is available. So it generally constitutes the higher order bits. So this is what tag is. Now what will index do? Index is used to select the particular set. For example, in this case index will not be very useful, because our each of the set has only one block. Now you can think of, so I can draw a situation. Let us say these two blocks constitute set 0, and then the next two blocks constitute set 1. So let me just call them set dash in a, let us say, 2-way set associative cache. Now for this set dash 0, the tag values will be same for both these blocks. Now how do you identify which block you want to specifically work with? That will be identified by the index. So in that case the index will tell that okay, and generally this index is this bit value. So there will be some other things like let us say valid bit and all these things. So if you want to invalidate the data, so you can just flip that bit to indicate. So I am not showing valid bit and all the other things. So the index will tell that okay, in the set which particular block you are looking at. Okay, and then the offset will tell us which 8 byte you are looking at. Okay, so in this case you have 8 bytes. So to identify which byte you are looking at, so you will need that offset value. Okay, so offset value will tell that okay, if you are looking at this particular byte or some other byte in the block. So I hope this makes sense. So tag tells us at a broad level like the block address, index tells us that and for the tags will be same for blocks in the same set. To identify which particular block in the set you are looking for, that is done by the index, and then the offset tells us which particular data block you are looking at. Okay, I hope this makes sense. So in case of a direct map cache, your index will not play any role, because in case of direct map cache your tag itself will be different for each of the blocks. Okay. So do let me know if you have any question. So what we have seen, we have seen that depending on where how the addressing is or how what kind of cache it is, our way of cache block identification also varies to some extent. So, if there is a set associative cache, their tag values in the same set will remain same, index will change, and that will tell which particular block in the set we are looking at, and then the offset tells us which particular block of data we are looking at. Okay. And in case of fully associative cache, of course you have to your tag will be different, and that will help you in identifying the particular where the particular block is. Okay. So, I hope this makes sense. Let me go ahead and talk about block replacement. Okay. And based on that, how we can classify the caches. So, by block replacement, we are trying to answer which block to replace this question. Okay. Now, this question can be answered in many ways. So, and depending on what kind of cache you are looking at, this choice will also vary. For example, which block to replace, this answer will be very obvious if you are looking at a direct map cache. So, in direct map cache, a particular block can go into a particular location only. So, which block to replace? You know that okay, this block can go in only in this location. So, that particular block has to be replaced. So, you do not have any choice in case of direct map cache. So, just to make sure that you appreciate this. So, for example, let us say I want to bring in block number 12 in this direct map cache, which block I should replace? Or basically there is no choice, because my block number 12 will come here. So, whatever is there, that has to be replaced. That is what we are trying to say. So, basically no choice in a direct map cache. Right. Now, going forward, in case of a associative cache, in case of an associative cache, which block should be replaced? That will be basically determined by basically whenever. Okay. So, in an associative cache, which block from the set should be evicted when the set becomes full? That is the question we have to answer now. So, what is the question? In a associative cache, so basically set associative cache, we have multiple blocks. Now, which block from these multiple blocks should be replaced or evicted when this set becomes full? So, so again, if I come back to this example, so let us say I want to bring in block number 12 in a two-way set associative cache. Block number 12 can come, let us say, in the first block in this set. I want to bring in block number 4. Block number 4 can come in the second block of this set 0. Now, let us say I want to bring in block number 20. Block number 20 also should come to set 0. Now, I have to replace one of them. I have block number 12 here and block number 4 here. I need to bring in block number 20. So, I have to now first replace one of them. Now, which one I should replace now? So, that is the question we have to answer. Okay. So, in in an associative cache which block from the set should be evicted when the set becomes full. Okay, so this is the question. Now, so coming back to this example again, so I have block number 12 here. So let me draw it. Okay, so I have block number 12, let's say, placed here, and block number 4 placed here, and now I want to bring in block number, let's say, 13, 14, 15, 16, 17, 18, 19, 20. So this is block number 20, so I want to bring in block number 20. So what should be the strategy? So one very simple strategy could be, I just randomly evict one of them and place the new block. So the strategy which we can adopt is random. And you will know, basically, if you study about it more, you will see that though it sounds like, oh, I am randomly replacing, but the performance is not very compromised in case of a random replacement strategy as well. So it's a very viable alternative. So you can just randomly replace one of them and get along with it, and your performance or your you will not have too much difficulty. The advantage is that the replacement policy becomes very simple, because you just maybe do some random event, and based on the outcome of that event you take which block, you decide which block to be replaced. So this can be one strategy. Now then can be another strategy which is very widely used, which is called least recently used. Okay, and the basically abbreviation is LRE. So least recently used, this sounds like a very logical approach, that okay, coming back to this example, I have these two blocks, I need to bring in a new block. Now among these two blocks I will figure out like which is the block which is not which is the least recently used. Okay, so out of these two blocks, which is the block which has not been used for longest period of time, and I decide that okay, that is the block, it's very likely that it will not get used. And because from our earlier discussion on temporal locality, we know that the block which is more recently used, it's very likely to be used more compared to the block which has not been used for quite some time. So with this thing in mind, we can replace the block which is least recently used with the new block which we want to bring in. So we will evict the block which has not been used for longer duration, and in that place we will bring in the new block, because it also preserves our temporal locality. So you can so basically it preserves temporal locality, so you can keep a note that all right. So now, is there any challenge in implementing this LRU scheme? There are few challenges. So for example, you need to keep a very close track of the usage of different blocks, and this usage value should be updated very frequently, right? Because if I like every time these blocks get used, I have to have some kind of a tracking mechanism which tells me which is the block which is more recently used, which is the block which is least recently used. So for a two-way set associative cache, it's still not a big deal. I can have a very simple mechanism that whenever I access the block, I'll just set a flag for that block which indicates that this is the block which is most recently used. So the other block will be the least recently used. But think about it, when you have let us say 4-way set associative cache or 8-way set associative cache. Now you have to keep track of, let us say, 8 blocks, and out of those 8 blocks, which block was used at what time. So it becomes very the overhead of keeping this information becomes very uh, significant. So you can't really keep up that whole information. It will add lot of overhead, and then also while you need to take a call about which block need to be replaced, you have to go through all the 8 blocks and look at their possible timestamp to figure out like when these blocks were used last and compare them, and then finally you have to take a call that which block to be evicted. So basically true implementation of this LRU scheme is only feasible for a very small set. Okay, because otherwise you need very fine grained control. Every load store will require to be tracked and all these things. So just to highlight all these things, I'll list out these observations. So first is LRU cache state must be updated on every access, right? So that you can have all the information, which one was used last and all these things. All right. Then basically true implementation only feasible for very small sets like 2-way set associative cache, etc. Okay. Now okay, so we understood that this is tricky to implement as it is in its true sense. So now something intermediate can be also thought of, which is called pseudo LRU. So in pseudo LRU, you don't actually keep track of all the blocks and their usage, etc. Your objective should be only to figure out the block which is the least recently used. So you can instead of keeping track of all the blocks, you can just keep track of the few blocks which are least recently used and implement something called pseudo LRU for basically 4-way or 8-way set associative caches. Okay. So this is one way out you can think of. So, in pseudo LRU you are not keeping track of all the status. You are just keeping track of few which are the potential let us say least recently used blocks. Okay. So, this is what least recently used or LRU scheme says, and based on whether your cache uses this kind of replacement policy, you can classify your cache as basically LRU cache, or let us say some other like random replacement policy cache and so on. Okay. The other possibility of this replacement policy can be first in first out, also known as round robin. Okay. So, first in first out or FIFO, and also known as round robin. So, what is it? Basically, as you can imagine that if we go back to the same example. So, here let us say the first block which was brought in was number 12, and then block number 4 was brought in. Now, whenever I need to bring in block number 20, I will apply first in first out. So, which one among these two blocks were brought in first? So, block number 12 was brought in first. So, it should go first. Okay. It should go out first. So, I will replace this block number 20 in the position of block number 12. Now, this actually is very easy to implement, and it also tries to make sure that all the blocks which you are bringing in, it remains in the cache for certain for a small duration, or for a certain duration, because every block will remain there for a specific period, because it is first in first out. So, in a round robin fashion, everybody will get their fair share of time in the cache, and this is also very useful for highly associative caches. So, in highly associative cache where you can't keep a track of which block was used at what time and all these things, you can easily implement this first in first out strategy. So, this is one strategy which is used. So, typically it is used in highly associative caches. All right. Now, basically the advantages here are easy to implement, and each block remains for a certain time. Remain in cache for certain time. So, it will never happen that you just brought in a block and then immediately you are getting rid of that block. Okay. Now, finally, the last replacement strategy could be not most recently used. So, this is quite interesting. So, it is kind of random, but here you can randomly choose any of the blocks to replace, but that block should not be the one which has been most recently used. Okay, or you can it can be random, it can be even FIFO. Basically you can apply the first in first out strategy, but first in first out strategy will not apply if this block, the one which is now supposed to be replaced, is the most recently used. So again coming back to here, let us say this block was brought in first, this block is second, and now I have to bring in the new block. Now if I just apply first in first out, I will replace this block, but I will, along with first in first out strategy, I will also apply another check where I will see that okay, according to first in first out, block number 12 should be evicted now, but among these two blocks, which one is the least, or which one is the which one is not most recently used. Now if block number 12 is the one which is most recently used, then though my first in first out strategy says that block number 12 should be evicted, I will not evict it, I will rather evict block number 4. Okay. So it here you are you can think of, you are applying FIFO, but you are along with FIFO you are also checking whether the block which is supposed to be evicted now, whether it is the one which is most recently used. If it is most recently used, then you will not evict it. So implementing this also is very not very difficult, because you have to just keep a track like which block is most recently used. So while your FIFO strategy tells that this is the block, but if that block is the most recently used one, then you will not evict it and you will go to the next block. Okay. FIFO with basically exception for most recently used blocks. All right. So I hope this makes sense. All right. Okay. So now we move to the final thing in the classification, which is the write strategy. So how do we write our cache? So how are writes handled? So just to make sure that we understand the context, so we are talking about this situation. So processor wants to write something, and now there can be different possibilities. So the data is already there in cache, or the block where the processor wants to write something, it is already there in cache. So in that situation, the processor can directly write it in the cache, and there can be one strategy where simultaneously it writes it to the main memory also, and this strategy is called write through. So basically you are writing whatever you are writing, you are updating it in the cache as well as in the main memory. So you write both in cache as well as in main memory. Generally it produces more traffic, but the design is very simple, because your main memory is basically always updated as you update something in the cache. So this is one strategy. The other strategy could be write back. So in write back, what you do, again the block is available in cache. So here we are considering only the situation where the block there is a cache hit. So whatever the processor wants to write, that block is available in cache. So in case of write back strategy, you will only update the content in cache. It writes only in the cache. And when do you update it in main memory? When that block needs to be evicted from your cache. That time, before eviction, you first update it in main memory and then evict the block. And how do you know that okay, there is something to be updated in the main memory? So whenever you write a block in the cache, you set a bit called dirty bit. So dirty bit indicates that the data is updated in cache, but data is not updated in main memory. So when you need to evict, you will look at the status of dirty bit, and if that dirty bit is set, then you will send the basically then before eviction you will update it into the main memory. Now there are advantages. So advantage is that you are not unnecessarily doing writes, and you are saving bandwidth, because remember that there are many intermediate results which actually there is no need to store in main memory, but in case of write through, everything whatever you update, it gets updated in main memory, and many a times it was possibly not required. In case of write back, you don't do that, you only update the main memory when you are evicting the cache block. But implementing it is little more complicated, the write back strategy, but you save bandwidth. So that is the advantage. Okay, so let me just write it down before we move ahead. So we will talk about the situation where there is a cache hit. So write through. So write through is basically write both cache and memory. So it produces generally higher traffic. But simpler to design. Okay. So this is write through, and in case of write back, so write cache only. Memory is written when evicted. So the dirty bit per block avoids unnecessary write backs. But it's more complicated to implement. Now in this context, I would like to highlight one thing, is that write back is more complicated, but it also provides more bandwidth, etc. So mostly you will see that high end processors uses write back strategy. But you guys will be already aware that we do not have one level of cache in most of the sophisticated processors. So you have multi-level of caches. So let's look at one example. Let's say I have, this is my CPU, and then I have my L1. So this is the first level of cache. Then I have L2. So L2 is little bigger. And finally, let's say I have only two level, and then I have my main memory, which is DRAM. Okay. So it has been observed, or if you look at the implementation of this high end processor, you will find that this CPU and L1 is very highly integrated. The L1 is almost like accessing data from L1 is very much like accessing data from registers and all these things. So this because they are so highly integrated, the strategy which is employed in this multi-level caches is that L1 and L2 are basically write through. So the first level and second level cache, they are write through. So basically whatever update you do in L1, it also gets updated in L2. Okay. But between L2 and DRAM, so this is more like write back. So basically you do not update whatever updates happens in L2 in your main memory directly. You wait for the data to get evicted, and then only you update it in DRAM. Okay. Why do you want to do that? Because you understand that this write through means you have to update it into the main memory, and updating it into the main memory will require time. And since this is very highly integrated, and basically if there is a write through strategy, then till the data is written, you have to basically stall your process. So your CPU performance will be significantly affected. So you don't want to do that. But if you are just writing the data into L2, that is very easy, because these are on the same chip, and basically whatever update L1 gets, that same thing can be reflected in L2 very easily. Also, you don't want to have difference between L1 and L2 primarily because in case of multi-cores, etc., the cache coherence becomes a very important aspect. So basically you need to make sure that if somebody else is using the same block of data which you are using, they get the appropriate data, or if you plan to use some data, you get the most updated data, and so on. So if let's say L1 and L2 were not write through, then there will be updated value in L1 which is not getting reflected in L2, and mostly the coherence protocols, etc., are implemented at this level of cache, so that your regular CPU pipeline does not get affected because of all these things. So to enable it, what you do, you make L1 and L2 as write through, so that everything related to the cache coherence protocol, etc., can be easily implemented using the updated value in L2, and L1 and CPU need not be bothered for those housekeeping stuff. But you do not also want to update every small thing in your DRAM. That's why L2 and DRAM are write back. I hope this makes sense. So this is write through, and this is write back. All right. So, this is something I just wanted to highlight. Okay, so far we have only talked about what happens when there is a cache hit. How about a cache miss? So, if there is a cache miss, so first of all, there is a miss. I want to write something in the cache. The processor wants to write something in the cache, and there is a cache miss. So, one strategy can be, which is called no write allocate. So, basically you directly go and update the main memory, that particular block in the main memory. There you are not allocating that block in the cache and so on. So, that can that can be one strategy. But here if you need to reuse that data, then again that is not a very good strategy, but it's simpler to use. Another strategy can be write allocate. So, in that case you fetch that block from main memory to cache and then write. So, so this is also a viable solution. So, two options: no write allocate, okay. So, basically you only write to main memory, okay. And in case of write allocate, you bring in that block. So, basically fetch block into cache and then write, okay. So, so what are the common combinations you will find in most of the caches? So, basically common combinations which are widely seen is basically you will have a write through and no write allocate. So, as you can guess, this is a very cheap one, and the performance is also not that great, because here you will be wasting lot of bandwidth, as well as if you are not exploiting the let us say temporal locality strategy in no write allocate, because you are not bringing in the data. The other combination, so this is generally used for simpler inexpensive machines. The other strategy or other combination can be write back and write allocate. Okay. So, this is for high performance. All right. So, these are the different ways based on like how we identify. So, basically these are the different ways we can classify cache. So, we have looked at how we can bring in a block into cache. Based on that, how we can classify different kinds of caches. For example, there can be fully associative cache, there can be direct map cache, or there can be set associative cache, based on how we want to place the blocks in the cache. The next thing we looked at is basically how the different blocks can be identified. So, basically you use your tag, index, offset to do that. So, for a set associative cache, the tag value will be same for all the blocks in the same set. The index will identify which particular block we are looking at, and then the offset will tell us which particular data byte we are looking at. Okay. So, depending on now what kind of cache you are dealing with, your either in case of let us say direct map cache, index will not have any meaning, because your tag will be sufficient to identify the particular block. Same for fully associative cache as well. So, after that we looked into the replacement policies. So, we looked at how we can, whenever we need to replace the blocks from the cache, how we can, what are the strategies. So, we looked at strategies like, so if there is a direct map cache, then there is no strategy. You have to, you do not have choice, you have to just replace that particular block where the direct mapping put that block. Then we looked into, in case of set associative caches, then you have the choice, like out of these blocks, which block you should be evicting. Now, their simple strategy can be randomly you choose any of the blocks. The other strategies could be you use the least recently used block, but we saw that for higher associativity like 4-way or 8-way set associative cache, keeping track of which block was used at what particular time, maybe the overhead may be quite high. So, there so you can implement LRU truly for very small sets, set associativity like 2-way set associative cache, etc. And if you go beyond that, then maybe you can use something like pseudo LRU, where you do not actually keep track of all the block and their usage. You just try to keep track of, let us say, the least recently used block. Then we also looked at other strategy like first in first out, where you basically replace the blocks in the order in which they were brought in. So, the advantage is that it is very easy to implement, and also each block stays for a certain duration in the cache. So, that also helps us in exploiting the basically temporal locality thing. Then we also looked at not most recently used strategy, where we apply first in first out, but if the block which is need to be replaced using the first in first out strategy is the most recently one, then we will not replace it and move ahead and replace the next one. So, this is what in terms of block replacement the different strategies or different classifications of caches are possible. And finally, we looked into the write strategy. So, basically how we handle the writes. So, in case of cache hit, we have seen that you can apply write through or write back. So, in write through, you also along with updating your cache, you update the main memory, but like many a times we do intermediate updates which do not get reflected finally. So, in those situations you will unnecessarily doing writes which will waste lot of bandwidth and also affect your performance. The other strategy, but write through is very simple to implement and most of the inexpensive machine applies that. The other strategy can be write back, where you do not immediately update the main memory, you just update the cache, and then when that particular block in the cache that need to be evicted, you indicate that if the block is updated, you indicate that using a bit called dirty bit, and if the dirty bit is set, then you basically go ahead and while evicting, before evicting, you update it into the main memory. So, that is little complicated to implement, but it improves the performance and you get better bandwidth utilization. If there is cache miss, then there are two strategies, like you do not bring the block in the cache and directly write into the main memory, which is called no write allocate. It is simple, but you do not exploit the temporal locality strategy there. And the other option could be write allocate, where you before basically if there is a cache miss, you bring the block into the cache and then only update or write it, and that is called write allocate. And finally, we also saw that especially for cheap processors, you tend to take the combination of write through and no write allocate. and in case of more performance oriented processors, you tend to take the strategy of basically write back along with write allocate. So, this strategy. So, these are the different classifications of cache based on these different characteristics. All right. So, we will resume our discussion from here in subsequent lectures.